Okay, so in this problem, we are going to be solving for the density of a log in water floating. So we can go ahead and start by labeling the length L. Then we can go ahead and give it a radius of R, and then the part that will be above the water from the top of the log down, that will have a value of H. So we know that the buoyant force is the force on the water upwards of the log. So we can go ahead and write out buoyant. And then we also know that the buoyant force is equal to the weight of the log. So you can go ahead and write out weight as well. So what is the buoyant force? The buoyant force is going to be the mass of the water times acceleration due to gravity, g. And the weight of the log will be very similar to the buoyant force. It will be the mass, this time, of the log, and then also times acceleration due to gravity. So, obviously, as you can see, two common variables, we can just cancel out the g's, leaving us with just the mass of the water equaling to the mass of the log. So, what does the mass of the water equal? The mass of the water equals the density of the water times the cross-sectional area below the water, which we'll denote as just like the little circle, or the little part circle that we have that is submerged underneath the water, and that will be multiplied by the length. And this time for the log, we have the density, but like I said, of the log, and our cross-sectional area of the log will just be the area of a circle, pi r squared. And this is still being multiplied by the length. So similar to the last one, the lengths don't really matter as like the g's. Go ahead and cancel those out. So we basically know all of our variables here, except for the cross-sectional area below the water. So if we just keep doing these little shapes, we know the cross-sectional area below the water is equal to the full circle area minus the little area above the water. Now, our only unknown variable is the part above the water, so we know that that is equal to the circular sector, which is just the area, like a little triangle underneath that, subtracted by the area of the triangle. So this will allow us to solve for the density later. Okay, so as you can see here, I have now drawn two other circles we will be using to help further solve. So we can go ahead and just start off by drawing our radius again, as well as our area above the water, which is h. And now, because we defined that weird like ice cream cone looking shape last time, we'll go ahead and add the other radius in as well, labeling that one r. And we'll have the area below the water above the center of the log. We'll label this r minus h. So we can also go ahead and label some angles now that we have this. So let me just redraw what we had above. And these angles, we'll call them theta. So now we can take the angle of the sector, which is 2 theta, and we will go ahead and divide that by the full amount of radians in a circle, which is 2 pi. And then we'll go ahead and multiply that by the area of the circle, which is pi r squared. So as you can see, 2's cancel out here, pi's cancel out here, leaving us with theta r squared. Now, our next step is going to be solving for theta, and we can do this by using arcsine. So we know that arcsine is adjacent over hypotenuse, so we have theta equaling, instead of arcsine, we'll just write cosine to the -1, looks a little better. That is equal to, like I said, adjacent over hypotenuse. So we have r minus h over r. All right. So now we can go ahead and substitute our theta back into the theta r squared. So we will get, r squared cosine, it's -1 of our radius minus our height over our radius. And this is the area of the little circular section. So now we need to go ahead and find the area of the triangle right here. So the area of the triangle is 1/2 base times height. So in our case, it's going to be 1/2 times our base, which we will just label as x, which will be this area right here. So 1/2 x, and then our height, as you can see, will be the r minus h, the radius minus the height. Okay, so now we need to solve for x, and we can use the Pythagorean theorem for this. So we will just use the side lines. So it is just one side line, which would be x squared, plus the other side line, which is the r minus h. That is squared as well. And then that is equal to our radius squared. Let me just fix that up a little bit. Okay, so now, like I said, we're going to solve for x. So we'll move our radius minus height squared over to the other side, and we'll take the square root. So that will leave us with x equaling the square root of r squared minus radius minus height squared. And this will take us into the next part. Okay, so now we are going to simplify our x a little bit more. So we can go ahead and multiply out the r minus h squared, and it'll get us negative r squared, so the r squareds will cancel. It'll get us a positive 2rh instead of minus, because of the minus on the outside. And instead of the h squared being positive, it will be negative. So we can just rewrite that, like I just explained, as x squared equals 2rh minus rh squared. So now that we have this, we have to substitute this back into our triangle formula, or the area of our triangle. So the x just goes into this x. So we will have 1/2, plug this into the x like I said, and then times r minus h. But since this was only solving for one triangle, this entire thing will be multiplied by 2, because we are looking at both of the triangles over there. So this 2 will just cancel out this 1/2. So finally, we need to take the circular sector and subtract it from this. So we will get r squared, circular sector, which is right here, I have it written in, times cosine, or arc cosine of -1 times r minus h over r. And this is going to be subtracted from what we just solved for, giving us the little top part above the water. So we'll give 2rh minus h squared multiplied by r minus h. So to find the area beneath the water level, we will take all of this and subtract it from the area of the circle, which is pi r squared. So I'll go ahead and write that out here. Let's make that a little smaller. And then all of this is going to be in parentheses. R minus h over r being subtracted from 2rh minus h squared times r minus h. So now we are extremely close. Our next step is to multiply all of this by 1,000. And this is the density of the water, which is 1,000 kilograms per cubic meter. And finally, our last step is to just divide by the area of the circle. So pi r squared. And here we go. This is the density of a log floating in water. Thank you very much for watching, and I will see you in the next video.